So far in the class, we haven't been able to deal with things like square roots of negative numbers, right? So whenever we've gotten to that, we've kind of stopped and said we can't take square root of a negative, so that's where we're going to stop. There's not a solution to this. But there actually is a way to deal with these, particularly dealing with the square root of -1. This is what we call our imaginary number I. So we can go into this whole world of what we call imaginary numbers. And that's exactly how we're going to interpret that. Every time we see the I, we're going to interpret this as the square root of -1. So now if I end up taking a radical like this, something like the square root of -4, if you remember our radical rules, we said if we can split this up into multiplication, this would really just be square root of 4 times -1. And then we said since the square root is really just an exponent to the 1/2, we can actually split this up, right? Since it's over multiplication and not addition or subtraction. So this is really the square root of 4 times the square root of -1. And so I can actually end up writing the square root of -4 is just 2 times I. And it turns out that even though this is an imaginary number, it has a lot of applications, especially in like electrical engineering and a lot of equations they use. They can use the imaginary numbers and the math actually works out. So we call this the imaginary number part. This is part of a bigger system of numbers called complex numbers. So just to maybe do a couple more examples here, if I took something like the square root of -9, this I could just think of as 3 times the square root of -1, since the square root of 9 is 3. Doing kind of the same process here, breaking this up. But I can also do it with things that aren't perfect squares, so something like the square root of -5. I could just rewrite this as the square root of 5 times I. So I'm pulling out that 5 times -1, and then I can split that up into the square root of 5 times the square root of -1 and get to that square root of 5i. Most people are pretty good at just jumping from here to here. But if you need to do the longer steps, of course, you can always do that. So this leads us to a set of numbers. So far we've only been talking about real numbers. We've put everything into the real number category. But when we start dealing with imaginary numbers, we go into the complex number system. So complex numbers are always written in this form. A plus B times I. And so this is where it has two parts. We have the real part of the complex number, and then we have the imaginary part of the complex number. Now this might be minus as well, but we could just think that plus and negative is the same thing, right? So here's the question. If I give you a number like this, we know that 5 is a real number, but is it also an imaginary number? Or I'm sorry, I should say, is it also a complex number? And I should mention that A and B are always real numbers when I set up a complex system. So the only imaginary part is this I right here, the square root of -1. So A and B will always be real. So I guess the question is there a way to write something like 5 in this form of a complex number? Well, I can do a kind of trick, right? I can write this as 5 plus 0 times I. And this will just be equal to 5, right? And I can do this with any constant, right? If I take something like 103, I can still just rewrite this as 103 plus 0 times I. So what this means is that any real number is also a complex number. So if we were thinking about where this falls in the hierarchy of numbers, if you remember we had like integers and rational numbers and natural numbers, all of that fell inside of the real number category. Well, it turns out that any real number is also a complex number, okay, but not vice versa. Right, something like 3 plus 7i, this has an imaginary part to it, so we wouldn't say this is a real number, we would only say this is a complex number. But with all of our real numbers, we can rewrite them in the form of a complex number, so we'll say that all real numbers exist inside of the complex. So really the complex numbers is a much bigger set of numbers And we'll end up, once we figure out complex numbers, we can now get answers to a lot of problems that we weren't able to get answers to before. So some of the quadratics, that we put them in the quadratic formula, we end up getting square roots of negatives, so now we can actually take care of that. Okay, so when we're dealing with complex numbers, we can do arithmetic with them, just like we can do with real numbers. So for example, if I have 3 plus 2i, I can add that to another complex number, something like 7 minus 5i. And the arithmetic is exactly what you would think you would do with it. I can just think of this as 3 plus 2i plus 7 minus 5i. I'm going to combine the imaginary parts, and I'm going to combine the real parts. So I'm just going to end up getting 10 minus 3i. So we can kind of treat it, when we're doing the arithmetic, the addition and subtraction, we can kind of treat it the same way that we were treating our variables, our like terms. So the idea is if you're ever doing addition or subtraction or multiplication or anything with complex numbers, you should always end up with something in this form, a plus bi, a minus bi. So you never want to have more than 2 terms there. So even something like this, 7 plus I, then minus 3 plus the square root of 2 I. Here I can just do my normal distribution of the negative here. So 7 plus I, and this will be minus 3 minus square root of 2 times I. I can definitely combine the 7 and then minus 3 easy, right? This will be 4. But I can also combine these two as well, right? This is really 1 times I, if I think about that. So what would the b part of this be? If I were going to write it in the form a plus bi.
Minus 2i squared? Or the square root of 2i squared?
Well, remember that we're not multiplying these, so it would be squared together, right? It's just like we did up here, we just added the real part of it.
So 2 squared plus 1i.
Close, the square root of, negative square root of 2, right? So you can actually just think of this as plus 1 minus square root of 2, and all of that times I. Okay, so that, in this case, becomes the imaginary part of the expression, this entire thing. Because this is just a real number, right? 1 minus square root of 2, because square root of 2 is a real number, so 1 minus that is also a real number. So most of the time, you're not going to be dealing, well, I say that, you might deal with something like this, where you can't actually combine the expression, but a lot of times, especially in your homework problems, there'll be something more like this, where you can combine the i's fairly easily using integers and fractions, something that's not too hard to add. So addition and subtraction is pretty straightforward. Multiplication is also pretty straightforward. We have to deal with some other aspects. So for example, 2i times 3i, what would this be? Well, 2 times 3 is 6, right? So that's easy. What will I get with the i's here? It's
I squared?
yeah, it's not a trick question, right?
Okay.
Just I squared. But the thing is, I can simplify this further. You know what I can do to this? No?
Well, the i's were negative. If you take 2 negatives and multiply them, they're going to end up positive.
Okay. But be careful, remember what I actually is. This is square root of negative 1, right? So if I take I squared, I'm really taking the square root of negative 1 times the square root of negative 1, which would be the square root of negative 1 squared, right? So actually when I take I squared, it just turns into negative 1, since that negative 1 is an inside. So you were right in saying that we square something, it's going to be positive. But in this case, remember what's underneath the square root is negative, which is something we haven't dealt with before. So really, I can say that 6 times I squared, that's actually going to be negative 6. So anytime you end up with an I squared in there, you can keep going. In fact, anytime you end up with I to any power, you can simplify it farther. We'll look at that in just a second. Any of the powers we can deal with. So if I have, this is 2 monomials, if I have 2, I shouldn't say monomials, this is 2 just imaginary parts. I can also do it if I have it in the form a plus bi, so something like 2 plus 5i times 1 minus 3i. You have an idea of how I would multiply these together?
Would we use FOIL?
Yeah, again, we would just use FOIL, just the way we would do with 2 binomials, right? So I can FOIL this together and I'll get 2 times 1, which is 2, 2 times negative 3i, so minus 6i, and then 5 times negative 3i. Oh, I'm sorry, I guess I should do 1 times 5i, right? So we'll get plus 5i, and then 5i times negative 3i, this will be minus 15 I squared. So don't forget about that one. In this case, the negative 6i combines with the plus 5i, just to be minus 1i. And then what will negative 15i squared become?
15.
Yeah, positive 15, right? And again, that's because I squared is negative 1, so negative 1 times negative 15, positive 15. So I should just be able to write this as 17 minus 1i. So again, whenever you're dealing with these, no matter what kind of arithmetic, you should always end up back in that a plus bi form. In some cases, you might end up with no i's at all, like we did here, but it's still in that form, right? This is negative 6 plus 0 times i. Or if you have an answer that's just, say you get an answer that's just 2i, well again, that's 0 plus 2i, so it's still in that form that we're dealing with. So if you square I, you'll get negative 1. We said that's definitely true. But what about other powers of I? So we know that I to the first power, that's just I, that won't do anything. We've already decided that I squared is negative 1. So what about I cubed?
Have to end up at a positive.
Well, close. Let's break this down. I cubed is really maybe I times I squared. And we know what I squared is, right?
Negative 1.
So that's negative 1. So really, I can think of this as just negative I. Okay? So we're going to kind of, as we go, we're going to use what we already know to try to simplify the powers of I. So we'll get I for the first one to the first power, then negative 1 is I squared, and then anytime we see I cubed, it's just negative I. That's what we'll simplify to. What if we go another step, I to the 4th?
I squared times I squared, so you'd end up at 1.
Right, exactly. So this I can break down to I squared times I squared. Both of these are negative 1, right? And when I multiply negative 1 times negative 1, this is just 1. What about I to the 5th power?
I squared times I.
Okay.
So you'd end up at 1 times I.
Right. Or if you want to think about it more simply, it's just I to the 4th times I, right? Which will get you the same answer. Right? So this is I to the 4th times I, and we know that I to the 4th is 1, so we just end up getting I. We'll go a couple more. I to the 6th.
I to the 4th times I squared.
Okay. I to the 4th times I squared. So this will be I to the 4th we already know is equal to 1. And then I squared is equal to negative 1. So that's negative 1. I think you'll start to see a pattern here. I to the 7th, can you guess what it's probably going to be? Maybe if I do
I,
that. If it follows the same pattern, it should maybe be
Negative I.
Right. And let's see, this will be I to the 4th times I cubed, right? I to the 4th we know is 1, and I cubed, we said that's negative I, and sure, 1 times negative I is just negative I. So let's do one more. I to the 8th,
1.
probably going to be 1, right? We can prove that it's really I to the 4th times I to the 4th. I to the 4th is 1, and then I to the 4th is 1, and so we get just 1 here. So we get the same repeating pattern. I, negative 1, negative I, 1. I, negative 1, negative I, 1. So then the question is, what if I have to deal with a really big power of I? So for example, what would I to the 100th power be? But I don't want to have to go through and do all of this. Is there a more efficient way to figure this out? That's what we'd like to know.
Negative 1.
So why do you say negative 1?
If it's not divisible, well, it's even, so we know it's either going to be 2 or 4.
Okay.
100 is not evenly divisible by 4. Yes, it is, so it's 1.
Right, it's going to be 1, right? So if I wanted to, I could think of this as I to the 4th times I to the 4th. A bunch of times, right? 25 times. But each one of these is going to be 1, right? So it'd just be 1 times 1 times 1, etc., etc. And it's going to be equal to 1. What about I to the 17th power?
It's going to be odd, and I'm going to go with it's going to end up with I,
Okay. So why do you think that?
because it's not divisible by 3.
Okay. So yeah, you're kind of on the right track here. I could actually break this to I to the 16th times I, right? And I to the 16th I know is divisible by 4, right? I to the 4th, I to the 4th, I to the 4th, I to the 4th. And these will all be 1s. Because they're all I to the 4ths. And so I'll just end up with 1 times I, which is I. There's actually an easier way to think about it. If you just take what the exponent is divided by 4 and then look at the remainder. Okay, so for example here, if I divide 4 by 4, I'll get a remainder of 0. So anytime that you can take that top exponent divided by 4, if you get a remainder of 0, it'll always be 1. Okay, so the same thing here. We took 100, if we divide it by 4, we get 25 with a remainder of 0. Here, well, maybe it'd be best to go down here. 5 divided by 4 has a remainder of 1, right? So this one has a remainder of 1. Anytime you take that exponent divided by 4 and get a remainder of 1, it'll always be I. So here, if you think about 17 divided by 4, it'll be 4, and then with a remainder of 1, right? So that tells us it's going to be I. 6 divided by 4, this has a remainder of 2, and then 7 divided by 4 has a remainder of 3, and then when we get to 8, it has a remainder of 0 again, right? If you divide by 4. So these are really the only 4 things that can happen when you divide by 4. You'll either get a remainder of 0, 1, 2, or 3. And those correspond directly with what value should be. So a remainder of 0 means it'll always be 1. Remainder of 1 means it'll simplify to I. A remainder of 2, it'll simplify to negative 1. And a remainder of 3, it should simplify down to negative I. So we can now kind of deal with even bigger ones, right? If I took something like I to the 243rd power. If I want to figure out what this simplifies to, I know it's only going to simplify to one of these 4 things. So I'll just take 243 divided by 4, and I'll get 6 here. End up getting 6 60 with a remainder of 3, right? So I know that this should simplify down to just negative I. And that should make sense, right? If you think about dividing by 4, you're just asking like how many i's to the 4th are in there if you start splitting it apart. And if you do that, you'll end up with a bunch of i's to the 4ths, but then the one that you'll be left over with is just going to be I cubed, right? But all of these will be 1. And so you're really just multiplying 1 times I cubed, and you know what I cubed is. It's negative I. So that's really all we're doing here when we're taking that division. We'll do one more just for a good measure. I to the 502nd power. So we're going to just take 502 divided by 4. So 1, and then 4 goes into 10 twice, and 4 goes into 22 5 times. So we end up with a remainder of 2 here. So that tells me that it should come out to equal negative 1. So once you kind of learn the trick, they become pretty quick, right? But it's really funny if you don't know the trick, and like students are trying to figure out a long way. So it's definitely good to know the shortcut. So since I is a square root of negative 1, it's a radical. We talked about last time that we typically don't want to have radicals in the denominator of a fraction, so the same thing with i's. So typically if we have an I in the denominator of a fraction, we want to get rid of it by rationalizing that denominator, rationalizing that fraction. So we'll start with like a simple example here. If I have 5 over 2i, what could I do to this fraction to get rid of the I in the denominator? You probably want to multiply it by something, right? In this case, I could actually just go through and multiply by I, right? Like this. Because this will give me 5i, that's okay in the numerator, over 2i squared. And then 2 times I squared, that'll just be 2 times negative 1. And so I'm going to be getting 5i over negative 2, or I can just think of it as negative 5 over 2 times I. Because I could think of this again as I over 1, just pull it out to the side there. I also could have taken that same thing, and if I wanted to, some people like to do this, they like to always multiply by just whatever is actually in that denominator, so they multiply by 2i over 2i. And we should get you the same answer, right? In the top now we'll get 10i, and in the denominator we'll get 4i squared, which is just negative 4. And so this will simplify down to negative 5 halves I, or negative 5i over 2, same thing. So both of those should get you the same direction. I know a lot of times people like to always use whatever's there, because when we're doing the actual radicals, we just multiply by whatever the radical is a lot of times, if it's a square root. What about a more complex one? Something like this, 3 over 2 plus 3i. In this case, I can't multiply just by 3i, right? Because I'll have to distribute that out, and I'm going to put a 6i. It doesn't help me. The 3i times 3i would be nice. It would be 9i squared, which is negative 9. But I'll still end up with a 6i here. So, you have any ideas on that one?
Multiply by the 2 plus 3i.
Okay, let's try that. So 2 plus 3i? Over 2 plus 3i, right?
Mm-hmm.
So the top will get 6 plus 9i, and at the bottom I have to FOIL this, right? So 2 times 2 is 4, and then 6i plus 6i will be 12i, and then 3i times 3i, that will be 9I squared. So that one's okay, but I still got the 12I, right? Which are kind of in the same problem, the same boat. So this way doesn't work, right? Any other ideas? There's something we did last week that was helpful with the radicals. Remember that?
2 minus 3i?
Right, 2 minus 3I, which is the
Congruent or
conjugate, right?
There you go.
So if we multiply by the conjugate, of a complex number, it will always become a real number because the complex parts will go away. Because if you notice here, the outside two parts, the inner, the first, and then the last, they become real numbers. The problem was with the two inner, the outer and the inner parts of the foil, right? But here they should go away because we said that in conjugates, the middle two terms of the foil always cancel out. So that should happen here also. So here in the top, I'll get 6 minus 9i. And then in the denominator, I'll get 2 times 2, which is 4. Then plus 6i minus 6i minus 9i squared. So I'll leave 6 minus 9i on the top. 6i minus 6i, that cancels out like we hoped. And then negative 9i squared is really just positive 9, right? Because I squared is negative 1. So I'll end up with all this over 13. So that's going to be kind of our trick that we're going to use here. Now the problem is this answer in a plus bi form? Because that's how I want to write all of my complex numbers. It's not quite, right? But I could do something pretty simple to write it in that form. If I could just maybe divide that 13 into both of the terms. So really the technical way we should write this is I'll divide the 13 into the 6 and into the 9i because we have to because they're separated by subtraction. So this will really just be 6 over 13 minus 9 over 13 times I. And now it's in the complex number form where the real part is here and the imaginary part is here. We can do one more of these. So how about 1 plus I over 3 minus 4i. I want to rationalize this. Should multiply by, what are we going to pick?
3 plus 4i.
Right, so the conjugate of that would be 3 plus 4i. So 3 plus 4i over 3 plus 4i. In the bottom, I'll end up with 3 times 3, which is 9. I don't even have to worry about the outer and the inner parts, right? Because they're going to cancel out. So I really just am concerned about negative 4i times positive 4i. So that would be negative 16i squared. So be careful with the negative stuff here, because it'll still say the same. And then that negative 1 from the I squared will change everything after that. Up here, I do have to do the entire FOIL. So 1 times 3 is 3. 1 times 4i is 4i. I times 3 is 3i. I times 4i is plus 4i squared. So up here, see 4i squared, that'll be negative 4, right? And then minus 16i squared will just be plus 16, since it'll change the sign there. And so on the top, I end up with 3 minus 4, which is negative 1. 4i plus 3i is 7i. And then 9 plus 16 is 25. But again, I want to write it in the a plus bi form. So I'll just divide that 25 into both terms. So I'll get negative 1 over 25 plus 7 over 25 times I to get into my a plus bi form. I'm actually going to cut this real quick so I'm going to go to a different section. So. Is that showing up all right? I hope it's loud enough on here. I think it probably is.
Hope it's big enough too to see.